Okay, Kevin, how are you?
Doing all right, Dr. Hunter. How are you?
Yeah, very well. Welcome back. So we said that we would just start with some questions today. So do you have any questions you want to ask me? And let's see what I can do with them.
Yeah, I guess my first question is what is temperature and how is it really measured?
Yeah. Um, I think temperature is a very interesting thing because we all take it for granted that we know. Like if I go outside, yeah, it's hot or it's cold or it's warm or it's cooling down, right? And so we have many years of our lives of understanding, developing this intuitive idea of what temperature is. And I don't know in many chemistry courses where what I'm about to say comes out in a way that it finally made sense to me. And so I'm going to try to share some of that right now with you. So I'm going to share my screen. I'm going to take you to the place in Cengage where it's introduced. So in this chapter, Cengage gets into um, some of the important mathematical relationships relating molecular speed, mass, and temperature. And there was a time, Kevin, that you and I made a promise that in this course, occasionally people would learn to read formula for what they mean, and rather than just skipping over them or just kind of accepting. And this is one of those circumstances. So I want you to look at the third equation down there. It's 10.11 in here. It's this one right here. And it says that the kinetic energy, the average kinetic energy of a gas, but frankly, of anything, the average kinetic energy is directly related to the temperature. And I didn't really understand what that meant until just a few years ago, but it's really quite sweet. Basically, it says, as the temperature increases, the kinetic energy increases. As the temperature decreases, the kinetic energy decreases. But I would like to turn it the other way around, which is to say that temperature depends on kinetic energy. As the kinetic energy drops, the temperature drops. As the kinetic energy increases, the temperature increases. What that really means is that temperature is kinetic energy. So if I go outside on a warm day and it feels warm to me, it's because the molecules are moving fast. They're slamming into me more. And as they slam into me, I absorb some of the energy, right? They hit me if I'm moving slowly. They hit me and they slow down and they give me some of their kinetic energy. And now all of a sudden I got this energy. Now I feel warmer. And so if we could begin to understand that molecular motion really is temperature, and that when we look at a thermometer, it's not measuring temperature, it's measuring molecular motion, and it's measuring what changes in molecular motion. I'm going to draw you a picture of a thermometer.
Okay.
So I'm going to pin my video. Okay, so here we go. Here's a thermometer. And it's got these gradations down the side. They probably should be even, so I better put one in there too, and one in there. But nonetheless, it's measuring temperature, and it's filled with some liquid right here. So all of this is liquid, okay? And let's say that today it's measuring 10 degrees Celsius right here, okay? All right, so I take this 10 degrees Celsius, that's a little warmer than my refrigerator, and it's measuring here. So I take it outside on a nice warm day, and so I take it from where it's at 10 degrees Celsius, and I move it outside someplace where we don't know this yet, but let's say it's 20 degrees Celsius. Okay, we don't know because our thermometer hasn't had a chance to measure it yet. Well, outside at 20 degrees, the gas molecules are zipping around, right? They're zipping around nice and fast. And some of them, as they're zipping around, make it over here and they slam into the side of my thermometer. And because they slam into the side of the thermometer, they give up some of their energy to the glass in the thermometer. And so now this glass, which was at 10 degrees Celsius before, is hit by a particle that's moving really stinking fast. And so it gets a little bit of energy. So it starts to vibrate a little bit more. And you see my pen vibrating, and I'm trying to make it darker. And then, oh, now these molecules are, these glass molecules in the side of my thermometer, they're a little warmer too. And so they start vibrating. Oh, and now they slam up against the liquid that's in the thermometer, and they start to vibrate more. And so now they're vibrating more, and oh, and now they're vibrating more, and they expand and they fill up the thermometer a little bit more. So now my thermometer, the liquid that's in my thermometer is starting to rise. Oh, but it's still a really warm day outside. Let's switch to a different color. Here comes another gas molecule whipping around like crazy. Boom, slams into the side of the thermometer. Oh, now maybe these glass molecules on the side here were vibrating a little bit more, but they're still not vibrating the way that they will be once they get up to what that secret temperature is that we're going to record eventually. But they get some of that energy, and so they warm up a little bit more. They warm up and they vibrate a little bit more. They pass some of their energy off to the liquid inside. Now these ones can vibrate a little bit more. Oh, and there's a little more energy, and that glass thermometer, sorry, the liquid in the thermometer absorbs some of the energy and takes up a little more room. Hold it. Have I got another color? Oh, I got green. Apparently there's a green gas molecule out there. And it's whipping around like crazy still, right? Because it's still really warm outside. And it keeps on going and eventually slams into the side of my thermometer. Could be over on this side, doesn't really matter. But it causes more vibration in the liquid that's in the thermometer. It absorbs some of the energy, it expands, and it fills up a little bit more. And so these molecules out here that have all this energy, because they're at this secret temperature, the secret as of yet unknown temperature, they're going to keep on doing that, and this gas will, the gas will slam into the sides of the thermometer. The glass in the thermometer will impart some of that energy to the molecules that are in the thermometer, and they'll absorb it. They expand a bit, and they move further and further up the thermometer. So my thermometer will is starting to record higher and higher temperatures. For 25 Cannon points, undying loyalty. At what point will this process cease to occur from your and my perspective?
Well, if the unknown temperature is 20 degrees Celsius, then I think the thermometer should stop at 20 degrees Celsius.
Exactly. So it's going to stop at 20 degrees Celsius, which conveniently is right there, apparently. what luck. Anyway, and so it does it until these molecules in here, well, it's really all of these molecules in here, but I'm pointing up near the ones that I care about right now, until these molecules are at the same temperature as the molecules in the outside world. And so now when these gas molecules when the liquid inside this thermometer gets to be 20 degrees Celsius, now when the outside molecules slam into the thermometer, there's no energy to be transferred. There's no thermal gradient, and so there's no energy that comes back inside, and so the molecules don't rise anymore, and so we get stuck at 20 degrees, and you and I read the thermometer and we get to 20. And so if you can begin to think about oh, all I'm doing on a warm day is experiencing high molecular motion, more movement, more kinetic energy as those molecules slam into me. That's the way that I finally understood temperature. It's just a measure of how fast the molecules are moving. And a thermometer, all it does is you stick a thermometer in something until the temperature, until the energy of the molecules inside reaches the same energy as the molecules that are slamming against it. And that tells us what that particular temperature is.
Yeah, certainly. I think that's kind of a new interesting take on temperature, because like you said in the very beginning of this video, we just think of it as how hot or how cold something is. So this is definitely more on the chemistry on the more particulate level.
Yeah, and the reverse is true, right? Okay, you're really warm, right? Yeah, I gotta get to someplace cooler, right? I'm down in the basement where I'm working right now. It's a lot cooler. So I'm working hard, and it's a hot day outside, and my body temperature is 37 degrees Celsius, and I go into a room that's colder. Oh, well, when I do that, the molecules in my body feel the gas molecules slamming against them in that room, but they're a lot cooler than my body. And so as a result, when they absorb some of the energy from my body when they hit me, and they speed up a bit, so they go, let's call it 25 degrees up to 26 degrees, right? And I go from 37 down to 36, because as those molecules have slammed into me, they've absorbed some energy, so they've gotten a little faster, and they've taken some energy away from me. I've gotten a little cooler, and I guess I got a little slower, so to speak. And so if you can begin to think about temperature as being molecular motion, you can begin to understand why in chapter 10, that's showing you there, showing the equations again? Yeah. So that begins to tell you, oh, look, there is kinetic energy. That's directly related to temperature, right? Kinetic energy, directly related to the mass and the velocity squared, right? And so you can begin to look at these equations for the really special insight that they show, but you got to have some sort of conceptual understanding to go along with it as well. Awesome. All right. Thanks, Kevin.
Thank
Talk to you again
Dr.
soon.
Hunter. Yep, talk to you again soon.